Chapter 16 is on acid and base equilibrium. So chapter 15 introduced acids and bases, and mostly we talked about strong acids and strong bases, which completely dissociate. So a strong acid like hydrochloric acid is going to completely break apart into its ions. It has complete ionization. But weak acids and weak bases do not completely ionize. So like hydrofluoric acid, some of them split apart into the ions, but the majority of them reverse and stay whole. So they create this equilibrium reaction where you have all three components, your starting acid and your ions. So this chapter is going to focus on weak acids and weak bases since they're the ones that form these equilibrium reactions. So the most basic type of a equilibrium is when your acid or base reacts with water. So for example, just kidding. And so in this chapter, the first half, we're going to look at reactions of weak acids and bases, and then sort of the second half covers solutions that also have acidic and basic properties, and these are usually solutions of salts. So acid ionization or dissociation is when your acid reacts with water to produce your hydronium ion, which is your H3O+, which we can also just say is equivalent to the hydrogen ion. We can sort of shorten it, and the conjugate base. So for example, acetic acid and water. Acetic acid is my acid. Water is going to be the base in this reaction. So my acid is going to give the hydrogen to the water. So this acid turns into the acetate ion, which is the conjugate base. And then the water turns into H3O+, which is the conjugate acid. And this is an equilibrium reaction where all four components are present once we reach equilibrium. So the weaker the acid is, the smaller and smaller it ionizes. Now, one thing we want to simply measure for most acidic solutions is the pH. So in order to measure the pH, we have to know the concentration of your hydronium ions. And in this case, we don't know what that concentration is because we don't know how much of the acid actually dissociates. It's going to be a small amount. It's not going to be all of it. So we have to be able to first determine this concentration using other methods, and then we can measure the pH of it. Now, a lot of times when we write these reactions, we abbreviate because formulas for acids and bases can get very long. So in general, any acid can be written as HA. And then the conjugate base, once it has lost that hydrogen, we can write as A-. So you'll see that notation a lot, which just means a general acid and its conjugate base. Okay. So if we write this general reaction, it's a monoprotic acid, has one hydrogen, we can write an equilibrium expression for this, since it's an equilibrium reaction. So Kc is equal to the concentration of your products over the concentration of your reactants. Now, the amount of water, that concentration of H2O remains constant. So we can rearrange that where we move this water over here to the side with Kc. Because both of those things are relatively constant, at least for a given reaction. So we're left with this rearrangement. This product here, the concentration of water times the Kc for a reaction, is called the acid ionization constant, and we abbreviate that as Ka. So we have the simplification of an equilibrium constant for an acid reaction where we don't have to include water since it remains constant. So there's no point in adding it if it's not going to make any difference. So that's our general formula for a Ka expression. So KAs have been tabulated for a lot of different substances here, and here are lots of different ones. Your book has even more of them. So most things you can just look up what the Ka is. In general, you can tell a little bit about what the value of Ka is. The smaller the Ka value, that means the weaker the acid, which means the less it dissociates, or the less it ionizes. And then the opposite is true. The stronger the acid, the larger the Ka, the more it splits apart. For any electrolyte, we can measure something called the degree of ionization, which is how many of the molecules ionize in water. So I abbreviate degree of ionization as DOI. So we can measure the degree of ionization in a couple of ways. Ions produced an electric current, so we can measure it using electrical conductivity. pH can also be used to measure, since pH measures how many ions are present in your solution. Okay. So the degree of ionization is measured for an acid as the amount of hydronium ions you have at equilibrium versus your starting concentration of acid. So it's just like a proportion. How much of them break apart versus how much did you have to begin with. So if we have nicotinic acid, it's a weak monoprotic acid, and this formula is a little long, so if we abbreviate the anion, that's C6H4NO2, with NiC. So we can rewrite this as H and then NiC, just to make life a little easier. So our solution is 0.012 molarity, and we know the pH from a pH meter or however we measured it. And our goal is to calculate the acid ionization constant, Ka, for this acid. For whatever reason, we don't know what it is. Now, even though we started with a certain concentration, only a few of them actually ionize, and that's what the pH is measuring. So we don't actually know how much of the nicotinic acid we have left whole versus how much we have ionized. So we can abbreviate this reaction like this. HNiC is our nicotinic acid plus water, turns into a hydronium ion, and this is my conjugate base, A minus. So our equilibrium expression, or our Ka expression for this, is going to be H3O plus, my conjugate base, over my starting acid. So what I have to do is figure out what values to plug in there in order to figure out my Ka. Okay, so because these are equilibrium amounts, we can do an icebox. So my initial concentration, which was given to us in the question, is 0.102. Water, we don't even care about because it's not going to change. And then our initial concentration of our two products are both 0. These go down by 1 mole, up by 1 mole, since the coefficients are 1 for all of these things. So now let's plug those values into our Ka expression. X times x is x squared. Okay. Now the problem here is that we still have two things we don't know. Ka, which is our true question, and then we also don't know what x is at this point. So we have to be able to figure out what the x is, and we can do that from pH. So the formula for pH is that. We can also rewrite that as that. Just two different ways of writing the same relationship. So we're going to use the second version because we're solving for the H3O+. So 10 raised to the negative pH, which was given to us in our question, 3.39, is going to equal to whatever our concentration of H3O+ is, which in this case is going to equal 4.1 times 10 to the negative fourth. So in this case, that equals our H3O+, which is also going to equal our x as well. So now we know a value for x. So x squared Now notice that if you were to work out the denominator, you get exactly what you started with, right? How much it goes down isn't really affecting it. The amount of the undissociated amount basically remains unchanged. Now you could actually find that, but you don't have to because it pretty much doesn't change at all. Okay, so when we solve this for our Ka, we get a value of 1.4 times 10 to the negative fifth, which is our value for our nicotinic acid. To define the degree of dissociation, or DOI, we want to know how much H3O plus we have at equilibrium over our starting amount of our acid, so in this case HNIC. So our starting concentration is 0.012. Usually we return this into a percent, multiplying it by 100. So only 3.4% of our nicotinic acid actually dissociated. 96.6% remained completely whole. So a very, very small proportion actually broke apart. Once you figure out what Ka is, or if you have been given that, you can use that to solve for the concentrations of your HA, your A minus, or your H3O plus for a solution of different starting molarities, which is more useful. Then you can use that to figure out the pH once you have solved for H3O plus. So in the last example, the denominator, like I said, that X part was negligible because a very small amount of it actually dissociated. Right, when we subtracted here, this essentially ended up being the exact starting thing. So it allows us to do this simplification where we didn't even have to subtract that 4.1 times 10 to the negative fourth. Okay. So this simplification is very useful to us because if we don't have that, we'd have to solve it using the quadratic. So when can we do this simplification? If our initial concentration Ca over our Ka, if that is over 100, then that means our X is negligible. We have a very small percent ionization, and we can ignore that X part, and we can use that to simplify our calculations. So Ca is your concentration of your acid at the start. And then Ka, for these problems, you would have to be given that so you can solve for it. All right, I'm going to stop here for this part, and I'm going to finish part 1 with a different video.